Alrighty, in this video we're going through the practice test for sequences, series, and induction. So let's make a start. You got this sequence here, which looks to be arithmetic. And how can we tell? Well, the way that we tell is we just see if we got to adding something each time. So plus 3, plus 3, plus 3 seems to be arithmetic. So what you could do is say arithmetic sequence as we are adding on a constant amount each time. You can just say plus 3, something like that. How many terms are in this sequence? So we get up to 44. Now if you want Tn for an arithmetic sequence, it's going to be T1 plus n take 1 times the difference d. Now that just comes from this formula, and you'll get this formula sheet in the test. So 44 is going to be 5 is T1 plus n take 1 times 3. So 39, I'll rewrite again. Basically, like take 5 from both sides, you're going to get 39 equals n take 1 times 3. Therefore, if we divide by 3, n take 1. So I think that's 13 equals n take 1. Therefore, n is 14, something like that. Or, you can literally just look here. If 5 is the start, then it seems like 35 might be the 10th term. So 35, would be the 11th term. And then another 3 would get us to 14. Find the 10th term in the sequence. So T10 is going to be T1, so that's 5, plus 10 take 1 times the difference, which is 3. So it's going to be 5 plus 9 times 3, which is 5 plus 27, which is 32. There we go. That is the 10th term in the sequence. Just making sure I've got that all right. 32 appears to be correct. 5 is the first term. 9 times 3. Yep, that should be right. Tn is T1 plus n take 1. Yep. Cool. So basically the way you can do that is you can step it out. So that would be T4 is 14. T5 would be 17. T6 would be 20. T7 would be 23. T8 would be 26. T9 would be 29, and T10 would be 32. So it does check out. All right, find the sum of this sequence. So basically what you can use is either of the two formulas. I'd recommend this first one, n over 2, T1 plus Tn. S, n equals n over 2, T1 plus Tn. And we actually know what n is because we know how many terms there are. There are 14. So this is 14 over 2. T1 is 5. Plus 44. So that is 7 lots of 5 plus 44, which is 7 times 49, which is quite a big number actually. Seven times 49 is 343. Now, if you're going to want to get extra fancy and double check this on a calculator, you can actually do it in the summation mode. So basically our sequence looks like 5 plus, well, realistically, 1, 2, 3, 4. Yep, so it looks like, 5 plus x take 1 times 3 is how we define our sequence. And if we sum that from x being 1 all the way up to 14, then that should sum and give us 343 as well, which it does. That's good. All right, next thing we got here, it's really important we show the full working out. This is 5 plus 5 plus 5. Because when k equals 2, it's 5. When k equals 3, it's 5. And when k equals 4, it's 5. So that's 15. That's sum. All these you can double check on a calculator too. So this one here is arithmetic. So S of 20. So let's see. If k equals 1, then you've got 4 plus 3 times 1 equals 7. So that is T1. So S of 20 is going to be n over 2 T1 plus n take 1 times the difference. And that comes straight from the formula sheet here. 2 lots of T1 plus n take 1 times the difference should be. So this is, let's see, 20 terms over 2 lots of 7 plus 20 take 1 times the difference, which is 3. So that's 10 lots of 14 plus 19 times 3, which we can work out. 10 lots of 14 plus 19 times 3 gives us 710. And then we can actually check this properly though, because we can do the proper sum on our calculator. So this is going to be 4 plus 3x. Chuck a plus in the middle there. X equals 1 all the way up to x equals 20. So it's 710 as well. This one here. So basically, again, we can work out what T1 is. This is geometric. T1 is 2 times 3 to the 1, which is 6. So for a geometric series, Sn equals T1 r to the n take 1 over r take 1, which is going to be 6 lots of 3 to the 8 take 1 over 3 take 1, which is going to be 6 lots of 3 to the 8 take 1 over 2, and we'll see what that gives us. 6 lots of 3 to the power of 8 take 1, close bracket, all over 2, 19680. Again, we can double check that using a calculator. So 2 times 3 to the power of x, do that from x equals 1 all the way up to 8, and we should find that we get 19680, which is great. Next thing we got here is 5 times a third to the k to infinity. So essentially what we need to be doing is we need to do T1 again. It's 5 times a third to the power of 1, which I can just say is 5 over 3. Sn is going to be T1 times r to the n take 1 over r take 1. But that thing is essentially going to 0 as the power goes to infinity, because r is a third. So this is a probably better equation that I could have used is sort of the other way around for it. Or I can just literally use the infinite series equation, which is probably going to be easier, T1 over 1 take r. But if you use the finite series equation and just work with it, it falls out as well. So T1 is 5/3 over 1 take a third. So this is 5/3 over 2/3, which I think just gives you 5 over 2, which is 2.5. And we can sort of check this on our calculator. So if I do 5 times 1/3 to the power of x, and we go x is 1 all the way up to maybe 100, hopefully we should get something about 2.5. Yeah, we do, so that's good. All right, next step we got here, we got a ball bouncing on the ground. It's losing 90% of its height each time. So this bit will be 100 centimeters, but then this bounce here will only be 90 centimeters. So how high will the fourth bounce go? Well, to get each consecutive bounce, what you've got to do is you've got to take the original one. So we'll go with 100 here. There we go, 100 times 0.9 gives us that 90. And if we times 0.9 again, it gives us the 81. And if we times 0.9 again, it gives us 72.9. So in theory, if we times 0.9 again, we should get our next bounce height, which is 65.61. 72.9 times 0.9 is that. centimeters. How many bounces will it take for the ball to go up less than 50 centimeters high? Well, this is trial and error, so fourth bounce will be 65.61. The fifth bounce times 0.9, 59.049. The sixth bounce, 53.1441. And if we times it by 0.9 again, we should get 47.829. All right, so this is the seventh bounce. That's what it works on. Now, if you want to do it by hand, what you can do is you can go each bounce n is going to be 100 times 0.9 to the power of n. Yeah, so we want this to equal 50, 100 times 0.9 to the power of n, and then that would give you a half equals 0.9 to the power of n. Then the way we could solve an equation like that is to log both sides. Equals log 0.9 to the n. Then the n could come out the front. N log 0.9 equals log of a half. Therefore, n is going to be log of a half divided by log of 0.9, which roughly equals, and we'll see what that is. So log of a half divided by log of 0.9 should give us 6.578 up to 7. So like you'd have to round up to the seventh bounce if you want to do that, because the sixth bounce would be not enough, so the seventh bounce you need. Next we have explain why the ball's traveled that. So the drop is 100 centimeters. Bounce 1 going up is 90 centimeters. Bounce 1 going down is also 90 centimeters. And then the next two are 81 and 81. Bounce 2 up, bounce 2 down. So total is going to be 100 plus 90 plus 90 plus 81 plus 81. See what that is. 100 plus 90 plus 90 plus 81 plus 81. 442. Cool. What total distance will the ball travel when it comes to rest on the ground? So basically we're expanding this out forever. So what we can do is total is the sum of I equals 1 to infinity of, well, let's see. So this is 100 times 0.9 to the power of, I bet is k. Okay, plus the original 100 that we started with. So this will be bounced 1 through to infinity. And then this one here will be bounce 0, so to speak, because it's before the ball lands on the ground. All right, so this one here is going to be, let's see, T1 is 90. So that's 90 times 90 over 1 take 0.9 plus 100, which is 90 over 0.1 plus 100, which is, I think it's 1,000 centimeters. That's really cool. Let's see if we can do that. So let's just check to make sure we're on the right track. So sum 100 times 0.9 to the power of an x value from x being 1, and let's go all the way up to 100 bounces. No. I think this needs to be 2 times that. So that's going to be 2 times that. So I think that gives you 1900 centimeters. Let's just check that. X equals 1 to 100. So you get that, double it, and then add 100. Yeah, there you go. So the reason you double it is because that bit gives you up plus down, essentially. So 1900 centimeters. All right. Next we have here an induction proof that 8 to the n take 3 to the n is divisible by 5. So what you need to do is you need to start by saying let Pn be the statement. 8 to the n take 3 to the n is divisible by 5. So we're going to prove that P1 is true. 8 to the 1 take 3 to the 1 is 5. This is divisible by 5. Therefore, P1 is true. Assume PK is true. So 8 to the k take 3 to the k is divisible by 5. Therefore, 8 to the k take 3 to the k is 5a for some a in z. Therefore, if we rearrange this, 8 to the k is 5a plus 3 to the k. We'll label that with star. I might actually do my star in a different color, just so we can see it. Cool. All right. So step 1. Step 2. All right, step 3. Pk plus 1. All right, so we need 8 to the k plus 1. Take 3 to the k plus 1 is 8 lots of 8 to the k. Take 3 lots of 3 to the k. And you can say here index laws. This is 8 lots of 5a plus 3 to the k. Take 3 lots of 3k. This is using star. It's using the induction step. Next we can expand it out. 40a plus 8 lots of 3k. Take 3 lots of 3k. Expanding. So that's 40a plus 5 lots of 3k. This can be like terms. Equals 5 lots of 8a plus 3 to the k. This can be common factor of 5. This is in Z as A is in Z and K is in Z plus. Therefore, PK plus 1 is true. Therefore, by induction, 8 to the n take 3 to the n is divisible by 5 for all n in Z plus. Great. Lovely induction proof. All right. Next, we have this matrix here, and we want to calculate a squared. A squared is 1111 times 1111, which is 1 plus 1. So that would be doing the first row, first column. You get 1 plus 1 there, 1 plus 1 there, 1 plus 1 there. This is 2, 2, 2, 2. Now, if you want to do that properly, you can jump into matrix mode. We can enter our matrix here. Very exciting matrix. Exit, exit. So shift matrix alpha A squared should give you 2, 2, 2, 2. So that's right. And then the next powers are shown here. And it appears that our conjecture, well, these numbers are 2 cubed, 2 to the 4, and 2 to the 5. So it appears that a to the n is all of your 1 less powers of 2. Because here when it's 6, we get 5. Got to be really careful, it's off by 1. 2 to the n take 1, 2 to the n take 1. All right. Prove your conjecture is true using mathematical induction for all n in z plus. Let Pn be the statement. A to the n is 2 to the n take 1, 2 to the n take 1, 2 to the n take 1, 2 to the n take 1. Cool. So P1. A to the power of 1 is 1, 1, 1, 1. This can be our left-hand side. And on the right-hand side, we get 2 to the 1 take 1, 2 to the 1 take 1, 2 to the 1 take 1, 2 to the 1 take 1. Giving you 2 to the 0, 2 to the 0, 2 to the 0, 2 to the 0, which is 1, 1, 1, 1. Therefore, P1 is true. So step 2 will be to assume pk is true. Therefore, a to the power of k is going to be 2 to the k take 1, 2 to the k take 1, 2 to the k take 1, 2 to the k take 1. Now we'll look at pk plus 1. So we're looking at a to the power of k plus 1. Now we'll do a want to show here. Want to show. We want to get 2 to the k plus 1 take 1. 2 to the k plus 1 take 1. 2 to the k plus 1 take 1. And 2 to the k plus 1 take 1. These just all simplify down to. So I was thinking my want to show is like my right hand side that I'm trying to get to. These should all simplify down to 2 to the k, 2 to the k, 2 to the k, and 2 to the k. So ak plus 1 is going to be split up into a to the k times a, which is 2 to the k take 1, 2 to the k take 1, 2 to the k take 1, and 2 to the k take 1, times 1, 1, 1, 1, using star, and this can be star as well. All right, so this is, we do our straight matrix multiplication. I get 2 to the k take 1 times 1 plus 2 to the k take 1 times 1. Make it really clear that you're doing this properly. Then on the next row, we get 2 to the k take 1 times 1 plus 2 to the k take 1 times 1. Same thing here. So this is going to give us 2 lots of 2 to the k take 1 in each spot. Which is 2 to the k, 2 to the k, 2 to the k, 2 to the k. Done. Therefore, p of k plus 1 is true. Therefore, by induction, a to the n is 2 to the n take 1, 2 to the n take 1, 2 to the n take 1, and 2 to the n take 1 for all n in Z plus. All right. Hopefully new induction thing. So basically we want to prove this statement now. So for all n in Z plus. So let Pn be the statement two plus 4 plus 8 plus all the way up to. Now if you want, you can do this with summation notation. This is I equals 1 to n of 2. I use k. K equals 1 to n of 2k. But yeah, we'll just do normal notation here. Plus 2 to the n is 2 to the n plus 1, take 2. This is the statement we're trying to prove. So let's look at P1. On the left-hand side, we get 2, which is just 2. On the right-hand side, we get 2 to the 1 plus 1, take 2, which is 2 squared, take 2, which is 4, take 2, which is 2. Therefore, P1 is true. Assume PK is true. Therefore, 2 plus 4 plus 8 plus all the way up to 2k is going to be 2k plus 1, take 2. Now we'll look at our pk plus 1. First thing I'll do is I'll label that with star, and then we're going to do a want to show. So want to show, in other words, what we want our right hand side to look like is 2 to the k plus 1, take 2, which should simplify down to 2 to the k plus 2, take 2. All right, so pk plus 1. So we're dealing with 2 plus 4 plus 8 plus 2 to the k plus 2 to the k plus 1. Now, all of this thing here is 2 to the k plus 1, take 2. Plus 2 to the k plus 1. Now this is using star. Now if we collect like terms, this is 2 lots of 2 to the k plus 1, take 2, which is 2 to the k plus 1, take 2, which is 2 to the, and this is using index laws. This is 2 to the k plus 2, take 2. Good. All right, next bit we have on this question is, you may have noticed it's a geometric sequence. So here we have T1 being 2 and R is also 2. So here's a formula for geometric sequence. This will be on our formula sheet here. We use this one. Sn equals T1 R to the n take 1 over R take 1. Which is 2 times 2 to the n take 1 over 2 take 1, which is 2 times 2n take 2 all over 1, which is 2 to the n plus 1 take 2. Yeah. So that matches what our conjecture actually was, so that's cool. The last part's a little bonus question. You don't need to be able to do this, but it's fun anyway, so we'll prove it. And this is proving that this formula works in general for any geometric series, not just the one we've been looking at up till now. So basically, prove that the sum of the series is Sn. So let Pn be the statement. All right, so we're going to be really careful about this. T1 plus T1R plus dot 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 T1R to the n take 1 equals T1R to the n take 1 over R take 1. So that's our Pn statement. P1, or in other words, n equals 1. On our left-hand side, we're going to get t1, that's it. And on our right-hand side, we're going to get t1 r to the 1 take 1 over r take 1. Now these two will cancel off. So you're just left with t1. Therefore, p1 is true. Assume pk true. Therefore, t1 plus t1r plus t1r to the k take 1 equals t1 r to the k take 1 over r take 1, and we're going to call that star. All right, so basically, now we got to look at another bit. pk plus 1, and we'll do our want to show. Want to show, or in other words, the right-hand side should look like this. t1 r to the k plus 1 take 1 over r take 1. That's what we're trying to get to from the left-hand side, which is all this stuff. t1 plus t1r plus t1 r to the k take 1 plus t1 r to the k. So we've added on that other term. Now all this stuff is going to equal t1 r to the k take 1 over r take 1. This will be using star. Now we're still adding on t1 r to the k at the end. All right, so a couple things you can do here. So we do have a common factor. We can pull out t1. I'd also like a common denominator. So what I'm going to do is something called cross multiplying, which is essentially I'm going to times this right-hand side by r take 1 over r take 1. And that gets the things on the bottom of the fraction the same. So this is t1 r to the k take 1 plus t1 r take 1. Sorry, that's r to the k. All over the same denominator, r take 1. So we get t1 out the front. And what I'm left with is r to the k take 1 plus, and we'll expand this in, r to the k plus 1 take r to the k. So this is common factor of t1. And then this is, cross multiplying. So now the r to the k's will cancel out. So you're going to get t1 lots of r to the k plus 1 take 1. So they're gone. Over r take 1. And oh my goodness, it matches. Therefore, pk plus 1 is true. Therefore, by induction, t1 plus t1r plus t1r to the n take 1 is t1 r to the n take 1 over r take 1. So we've just proven that the formula for the geometric sequence series thing actually works. Very fun.